Hello everyone, this is Jayavarshit of CXE section B. My topic is skew complement of M matrices. In linear algebra and theory of matrices, the skew complement of a block matrix is defined as follows. Suppose PQ are non-negative integers and suppose A, B, C, D are respectively P into P, P into Q, Q into P and Q into Q matrices of complex number. Let M equal to matrices of A, B, C, D. So that M is a P plus Q into P plus Q matrix. If D is invertible, then the skew complement of the block D of matrix M is the P into P matrix defined by M by D equal to A minus B D inverse into C. If A is invertible, the skew complement of a block matrix of M is Q into Q matrix defined by M by A D minus C into A inverse into B. In the case that A or D is singular, substituting a generalized inverse or the inverses on M by A and M by D yields the general skew complement. The skew complement is named as Isai skew, was used to prove Skew's lemma, although it had been used previously. Emily Virginia Hansworth was the first to call it the skew complement. Skew complement is a key total in the fields of numerical analysis, statistics, and matrix analysis. In the background, the skew complement arises when performing a block Gaussian elimination on the matrix M. In order to eliminate the elements below the block diagonal, one multiplies the matrix M by a block lower triangle matrix on the right hand as follows. A is a matrix of A, B, C, D, where IP denotes a P into P identify matrix. As a result, the skew complement appears in the upper left P into P block. Continuing the elimination process beyond the point, that is performing of a black Gaussian Jordan elimination. Here we have a problem. A minus matrix of A minus B D inverse C of B O B 0D, which implies matrix of IP minus BD inverse O IQ into matrix of A minus BD inverse C BOD B0D equal to matrix of A minus BD inverse C 00D leads to an LDN decomposition of M, which reads M equal to matrix of ABCD, which is equal to matrix of IPBD inverse 0 IQ into matrix of A minus BD inverse C 0 0 D into matrix of IPO D inverse C IQ. Thus the inverse of M may be expressed involving D inverse and the inverse of skew's complement, assuming it exists as M inverse equal to matrix of ABCD inverse equal to multiplication of matrix IPBD inverse 0 IQ into A minus BD inverse C 00D into matrix of IP 0 D inverse C IQ whole inverse. Matrix of IP 0 minus D inverse C IQ into A minus BD inverse C whole inverse 00 D inverse into IP minus BD inverse 0 IQ, which is equal to matrix of A minus BD inverse C whole inverse minus of A minus BD inverse C inverse into BD inverse minus D inverse C into A minus BD inverse C whole inverse D inverse plus D inverse C into A minus BD inverse C whole inverse into BD inverse, which is equal to M by D in matrix of N by D inverse minus M by D inverse into BD inverse minus D inverse C into M by D inverse D inverse plus D inverse into C into M by D inverse into B into D inverse. The above relation comes from the elimination operation that involve D inverse and M by D. An equivalent derivation can be done with the roles of A and D interchanged by equating the expressions for M inverse obtained in these two different ways. One can establish the matrix inversion lemma, which relates the two score complements of m by d into m by a. See derivation from LDU decomposition in Woodbury matrix identity and alternative proofs. Properties. If P and Q both 1, that is A, B, C, D are all scalars, we get similar formulae for the inverse of a 2 by 2 matrix provided that AD minus BC is non-zero. M inverse is equal to 1 by A D minus BC into matrix of D minus B minus C into A. In general, if A is invertible, then M equal to matrix of A, B, C, D equal to matrix of IP 0 CA inverse IQ into A 0 0 D minus CA inverse B into IP into IP matrix of IP A inverse B 0 IQ. M inverse equal to matrix of A inverse plus A inverse B into M by A inverse into CA inverse minus A inverse B into M by A inverse minus M by A whole inverse C into A inverse M by A inverse. Whenever this inverse exists, when A respectively D is invertible, the determinant of M is also clearly seen to be given by det M equal to det A into det of D minus CA inverse B respectively. Det M equal to det T into det A minus BD inverse into C, which generalize the determinant formula for 2 into 2 matrices. Guttman rank additivity formula. If D is invertible, then the rank of M is given by rank M equal to rank T plus rank of A minus BD inverse into C. Now if we assume that M is symmetric, so that A, D are symmetric and C equal to B greater than, then we see that M is expressed as M equal to matrix of AB B transpose D equal to I BD inverse 0 I into A minus BD inverse into B transpose 0 0 D into I into BD inverse 0 I whole transpose, which shows that M is similar to a block diagonal matrix. Obviously the square complement of A minus BD minus 1B greater than is symmetric. As a consequence, we have the following version of Sturck's trick to check whether M0 for a symmetric matrix M, where we use the usual notation M0 to say that the M is positive definite, and the notation M0 to say that M is positive semi-definite. Proposition: for any symmetric matrix M of the form M equal to matrix of AB B transpose C, if C is invertible, then the following properties hold. First one, M 0 if and only if C 0 and A minus BC minus 1B greater than 0. Second, if C 0, then M 0 if A minus BC minus 1B greater than 0. Proof: observe that matrix of 1 BC inverse 0 1 whole inverse is equal to matrix of I minus BC inverse 0 I, and we know that for any symmetric matrix T and any invertible matrix N, the matrix T is positive definite if and only if NT N greater than, which is obviously symmetric, is positive definitely, then NT N greater than 0. But a block diagonal matrix is positive definite if and only if each diagonal block is positive definite, which concludes the proof. This is because for any symmetric matrix T and any invertible matrix N we have T0 if and only if Tn greater than 0. Another version of proposition using the square complement of A instead of the square complement of C also holds. The proof uses the factorization of M using the square complement of A. Proposition 2.1. For any matrix M of the form M is equal to matrix of AB P transpose C. If A is invertible, then the following properties hold. M 0 if and only if A 0 and C minus B greater than A minus 1B 0. If A 0, then M 0 if and only if C minus B greater than A minus 1B. Here is an illustration of proposition 2.1. Consider the nonlinear quadratic constraint Ax plus B transpose into Ax plus B greater than C transpose X plus D, where A belongs to Mn of real numbers, X, B, C belongs to real numbers, N and D belongs to real numbers, which obviously I equal to In is invertible and I greater than 0. We have matrix of I matrix of I into Ax plus B transpose C transpose X plus D greater than equal to 0. If and only of C to X plus D minus Ax plus B transpose A into Ax plus B greater than or equal to 0. If and only if Ax plus B transpose into Ax plus greater than or equal to C transpose X plus D. Since the matrix of A scalar C transpose X plus D minus Ax plus B transpose into Ax plus B is the square complement of I in the above matrix. The trick of using square complements to convert nonlinear inequality constraint into linear constraints on symmetric matrix involving the semi-definite ordering greater than equal to is used extensively to convert nonlinear problems into semi-definite programs. See Boyd, and when C is singular or A is singular, it is still possible to characterize when a symmetric matrix M, as shown, is positive semi-definite, but this requires using a version of the square complement involving the pseudo inverse of C, namely A minus BC transpose into B transpose, or the square complement involving the pseudo inverse of C, namely A minus BC transpose into B transpose of the square complement C minus BT transpose A transpose B of A. But first we need to figure out when a quadratic function of the form half xt px plus x transpose B has a minimum and what this optimum value is. Where P is a symmetric matrix, this corresponds to the general quadratic optimization problem. Minimize f of x equal to half xt px plus x transpose B, which has no solution unless P and B certain conditions. The square complement arises naturally in solving system of linear equations such as a, B, C, D, X, Y equal to U, V. Assuming that the submatrix A is invertible, we can eliminate X from the equation as follows. X equal to A inverse U minus BY. Substitution this expression into the second equation yields D minus CA inverse B into Y equal to V minus CA inverse into U. We refer to this an reduced equation obtained by eliminating x from the original equation. The matrix appearing in the reduced equation is called square complement of the first block A in M. S definite equal to D minus CA inverse B. Solving the reduced equation, we obtain y equal to S inverse into V minus CA inverse into U. Substituting this into the first equation yields x equal to A inverse plus A inverse B into S inverse C A inverse into U minus A inverse B S inverse into V. We can express the above two equation as xy matrix of xy equal to A inverse plus A inverse B S inverse C A inverse minus A inverse B S inverse minus S inverse C A inverse S inverse into matrix of U by V. Therefore, a formulation of the inverse of a matrix A B C D inverse is equal to A inverse plus A inverse B S inverse C A inverse minus A inverse B S inverse minus S inverse C A inverse of S inverse. In particular, we see that the Scar complement is the inverse of the 2 into 2 block entry of the inverse of M. In practice, A to be well conditioned in order for this algorithm to be numerically accurate. In electrical engineer, that is often referred to as node elimination or Cron reduction. Suppose the random column x, y live in r power n into r power n respectively, and the vector xy in r power n plus m has a multivariate normal distribution whose covariance is the symmetric positive definite matrix sigma equal to matrix of A B B transpose C, where A belongs to real number power n is the covariance matrix of X. C belongs to R into M is the covariance matrix of Y, and B belongs to R into N into M is the covariance matrix between X and Y. Then the conditional covariance of X given Y is Skull complement of C in sigma. Cov of X by Y equal to A minus B inverse into B transpose E of X by Y equal to E of X plus B C inverse Y of EY. If we take the matrix above to be not a covariance of a random vector but a sample covariance, then it may be a Weierstrass distribution. In the case, the Skull complement of C also a Weierstrass distribution. Condition for positive definites and semi-definites. Let X be a schematic matrix of a real number given by X equal to matrix of A B B transpose C. Then A is invertible. X is positive definite if and only if A and its complement X by V are positive definite. X greater than 0, A greater than 0, X by A equal to C minus B transpose A inverse B greater than 0. If C is invertible, then X is positive definite if and only if C and its complement X by C are positive definite. X greater than 0, C greater than 0, X by C A equal to B minus C inverse Bt greater than 0. If A is positive definite, then X is positive semi-definite if and only if complement X by A is positive semi-definite. If A greater than 0, then X greater than or equal to 0, X by A equal to C minus B transpose A inverse B greater than 0. If C is positive definite, then X is positive definite if and only if the component X is C, X by C is positive and semi-definite. If C greater than 0, then X greater than 0, X by C equal to A minus B C inverse Bt greater than 0. The first and third statements can be derived by considering by the minimizer of the quantity mu transpose A into mu plus 2V transpose B transpose U plus U transpose plus CV as a function of V for fixed U. For furthermore, since matrix of A B B transpose C greater than 0 implies matrix of C B transpose B A greater than 0, and similarly for positive semi-definite matrices, the second respectively fourth statement is intermediate for the first statement, respectively third statement. There is also a sufficient and necessary condition for the positive semi-definites of x in terms and generalized Kerr complement precisely. If a greater than or equal to 0, then a greater than or equal to 0, c minus b transpose a power 9 b transpose greater than or equal to 0, I minus a into a power 9 into b equal to 0, where a power 9 denotes the generalized inverse of a. Thank you.